So that is why we need multi-layer perceptron. Multi-layer perceptron has the ability to solve the limitations of using perceptron or single perceptron. Introducing the single-layer feed-forward perceptron, often referred to as a single-layer neural network or perceptron network. In this configuration, all inputs are directly connected to the outputs. The output unit operates independently with no shared weights among them. It's a straightforward architecture that processes information in a single pass, making it suitable for certain tasks but limited in handling more complex relationships between inputs. But as we have said, this single layer feed-forward perceptron can actually solve limitations of perceptron. We will see in the next slides how they can learn nonlinear functions. So let's take a closer look on the architecture of single layer feed-forward perceptron. So delving deeper into the single layer feed-forward perceptron, each unit in this network receives inputs exclusively from units in the immediately preceding layer. Furthermore, within the same layer, all nodes share the same activation function. This simplicity in connectivity and activation helps streamline information flow, but may pose limitations when dealing with intricate patterns and hierarchical representations in the data. And this is what we will see next in the advanced architectures. Anyway, in the figure here, we have a single layer feed-forward perceptron with one hidden layer. So the hidden layer has two nodes, 3 and 4. It has also two input units and one output. It's called also fully connected. Fully connected means that all the inputs are connected to all the nodes that we have in the hidden layer. Now let's understand how the output of our single layer feed-forward perceptron is calculated. For a specific unit, say E5, it's computed as, so E5 equal to the activation function phi applied on the sum of weights multiplied by values. So here we have the weights W3 5 multiplied by E3 plus BS3 5 plus the other sum of weights 4 5 multiplied by E4 plus B4 5. So here we have weights multiplied by inputs plus BS. So we sum all of them and we apply the activation function. This is the output. So here E5 is expressed in intermediate weights and bias. Then we can replace E3, which is the output of node 3, with its value. So we can backpropagate and compute all the variables according to their functions. So here we will have the same thing, but we will replace E3 by the activation function applied on the sum of W13 multiplied by E1 plus B13 plus weight 23 multiplied by E2 plus B23. Anyway, so we will not delve into all the computation because it's very easy to figure out that in each layer, for each output of a specific layer, we have the activation function applied on the previous sum. And we can replace E4, which is the output of node 4, with its value. And similarly, we will have this very long function in which we can express the output using the inputs of the single layer feed-forward network. So we can express the outputs, the final output, using the very initial inputs of the model. Anyway, here phi represents the activation function, and this nested structure showcases the step-by-step computation involving weights, bias, and activation functions in our single-layer perceptron network. It's like a series of interconnected decision-making steps that collectively determine the final output of our network. Consider that we have two classes. The first one includes yellow points, it is class 1, and the other class includes blue points and it can be labeled as class 0. In order to classify the points, we can use, for example, 5 perceptrons, where each perceptron is a line and then form the polygon with 5 laterals. This polygon is not a good classifier as it misclassifies 2 points from each class. So the best classifier actually should be nonlinear. For example, ellipse width. And in order to achieve this, we need to use a neural network with at least one hidden layer. As you can see here from the figure, it's very easy to understand why do we need a single layer feed-forward network. Because here we can learn non-linear function. So as I have explained, we could use 5 perceptrons where each perceptron is like a line. Connecting the lines forms a polygon with 5 sides. However, this polygon is not perfect. It makes mistakes on 2 points from each group. So in order to create a better classifier, we need something more flexible and non-linear, like an ellipse width. This is where a neural network with at least one hidden layer comes in. It can handle complex patterns and make better decisions, like fitting an ellipse width around our points for more accurate classification. Unlocking the true potential, neural networks with just one hidden layer are like magic. They can mimic and represent any shape or pattern. In simple terms, they are universal approximators. This means that they are capable of imitating any smooth and confined pattern, making them incredibly versatile in learning and capturing complex relationships in data. So it's a powerful capability here that we have using neural networks, but we have a catch here. Achieving a high level of accuracy in this approximation may require a large number of neurons, large number of nodes in the single layer, making it computationally expensive. So training such networks also requires a substantial amount of data. It's a balance between the incredible flexibility of neural networks and the resources needed to harness their full potential. So what you need to learn here is that using only single layer perceptron, we can approximate any nonlinear function, the one that we have seen before, for example, ellipse width or any other complex nonlinear function. But in order to achieve this, we need infinite number of lines, infinite number of neurons in the single layer. And this is very expensive in terms of computation. So we need to have many computations in order to learn the weights and the bias for each of the nodes, because it should be practically infinite. To overcome the limitations of a single layer perceptron, the multi-layer perceptron was introduced. By incorporating hidden layers, and in MLP gains the capability to understand more complex, nonlinear connections between inputs and outputs. This enhancement allows multi-layer perceptron to tackle real-life tasks like image recognition, speech recognition, and natural language processing, and also to solve many GUI problems. To get a sense of their learning power, we can explore the impacts of different number of hidden layers and activations functions by trying out this interactive playground. So I offer for you here an interactive playground where you can change different hyperparameters, for example, number of hidden layers and activation functions, in order to figure out how the learning is made, and also to explore the potential of using mini layers, using multi-layer perceptrons. Let's give an example of multi-layer perceptron. So in the first layer, we perform matrix calculation. Input vector x represents the initial data, so the initial input, and we have the weights matrix W1, which captures the importance of each input connection. We have bias vector B1, which adds an extra term to the calculations. And we have the output vector E1, which is the result after applying the activation function on the sum of W1 multiplied by X plus bias B1. So this matrix magic is the first layer. In the first layer is a fundamental step in the intricate dance of multi-layer MLP, in the multi-layer perceptron. I would like to stress that these transformations involve matrices, making it powerful and efficient process to capture intricate relationships within the neural networks. So here we will use, instead of using only weights, we will use matrix of weights. In each layer, we have matrix of weights and also matrix of bias. So the multi-layer neural network try to learn a function f that maps input x to output y. So the y, which is the output, should be equal to a certain function f that we are aiming to learn, applied on the x, on the input. Then the final mapping function is the activation function of weights multiplied by the inputs plus bias. So the final mapping function in neural network is a compound function involving the activation function applied to the weighted sum of inputs. In more details, so we have the weighted sum. So each input is multiplied by its corresponding weights, and these weighted inputs are summed together. Then we apply the activation function. The result of the weighted sum is then passed through an activation function, and the activation function aims to introduce, as we have said before and explained in many instances, tries to introduce nonlinearity and determines the output of the neuron or layer. This compound function, combining weighted sum and activation function, enables the neural network to capture complex patterns and relationships in the data. So you have this equation, which is y equal to fx, and where we change different outputs in different layers. So it's the function of x, which is the last activation function applied on the output of the last function, and so on and so forth. So we propagate the signal from the last layer to the first layer, and we replace all the weights and bias in each of the layers. So here WL, for example, means the matrix of weights in the layer L, and W2 is the matrix of weights in the layer 2, and W1 is the weight matrix of the weights in the first layer. Multi-layer perceptrons offer a dynamic approach to problem solving. First, the ability to navigate complex, nonlinear challenges sets them apart. Whether faced with small or extensive datasets, multi-layer perceptrons showcase versatility, providing reliable performance across varying input sizes. So they do not discriminate based on data size. Generally, whether you have got a handful of inputs or large datasets, MLP handles them well. However, if the problem is complex, if large datasets are actually required in order to achieve good performance. So in general, we don't need to have very large datasets when we use a multi-layer perceptron, but if the problem is complex, then we need sufficient data. We need large datasets. One notable advantage lies in the swiftness of obtaining predictions post-training. This efficiency contributes to their suitability for tasks demanding both speed and accuracy. Speaking of accuracy, MLP demonstrates a consistent performance ratio, adept at maintaining precision with both large and small datasets, and this is particularly if we compare them with classical statistical methods. However, MLP have also some drawbacks, and we can call them actually limitations. So the computational domains of MLP can be substantial, leading to time-consuming and intricate processes. So for complex problems, MLP actually require a huge time in order to train the model. Additionally, predicting the impact of the dependent variable on each independent variable can be a formidable task. The model's effectiveness hinges significantly on the quality of its training, making robust training practices essential for optimal performance. These considerations shed light on the nuanced landscape of MLP, where advantages and challenges coexist in the pursuit of effective problem solving. So now let's talk about the challenges. Multi-layer perceptron have a knack of being a bit computationally demanding and intricate, as we have said. So it's like asking them to solve a puzzle that takes like a bit of time. Predicting how much one variable affects the output is also another challenge. So, well, that's a bit tricky for MLP. They struggle to precisely measure the impact of each factor, of each input feature. This is one of the challenges actually. So it's very hard to learn the importance of the features using MLP. It's not like the classical methods where the statistical methods where we have clear formulas and it's very easy to understand which feature is very important to make decision of the final output. So it's tough. So it's tough to them to predict how much the dependent variable affects each independent variable. Lastly, their performance heavily leans on the quality of their training. So it's like saying you are only as good as your practice. This breakdown provides insights into when and where MLP shine, as well as their challenges and limitations. Now, let us move on to the training process and how MLP learns from data. The neural network learning process is a fascinating journey of adjustment and refinement. It's a workflow with 3 steps, repeated until perfection. The first step is forward propagation. Imagine taking a step forward. In this step, the network makes predictions based on its current understanding. So, in the forward propagation, the neural network aims to make predictions. Then, in the second step, it measures the error. So the second step is measurement of the error. We evaluate the performance achieved by the model so far, and we check if the prediction made are correct or not, and how much and how many predictions are correct. We measure the difference between our predictions and reality. The third step is backpropagation, which is the most crucial move. This step involves learning from mistakes. We adjust the model parameters, weights, and bias based on the measured error, refining the predictions for the next iteration. This iterative improvements and trial and errors and optimization will guide the neural network toward mastery. So the goal is to achieve the best possible performance in understanding and predicting patterns in the data. So let's explain these three steps one by one. Our neural network adventure begins with the initialization of weights, the starting point for the network's learning journey. It's like tuning instruments before a musical performance, a crucial step for a harmonious outcome. Anyway, just like giving a starting point for any task, weights in the network need their initial values. The choice here significantly influences how quickly the network learns and its overall performance. Common weights initialization techniques include random initialization. It's like random tune-up, setting weights to random values. We have another approach which is Xavier initialization. It's a bit more calculated, ensuring balanced weights for smoother learning. There is another approach called He initialization. It's a bold approach preparing weights for networks with rectified linear units with ReLU activation functions. The proper initialization has impact on the learning convergence. In fact, proper weight initialization can lead to faster convergence during training and better overall performance of the neural network. Here is the secret. Proper weight initialization, it's like finding the right rhythm. It can make the training process faster, leading to quicker conversion. Moving forward in our exploration, the forward pass takes center stage. During this phase, input data traverses through the layers of the neural network. Each layer applies mathematical operations, transforming the input into a new representation. It's the core mechanism that turns raw data into meaningful insights and patterns. We have already explained how output of each layer can be computed and how the final output can be computed. So, forward propagation is the fundamental process of transmitting input data through the neural network. During this stage, the network computes the weighted sum of inputs, applies activation functions, and generates an output prediction. It's the initial step in the neural network operation after the weight initialization, where the network transforms input information into a meaningful predictions. In the second step, we calculate the loss or error by comparing the predicted output with the target output. A crucial aspect here is the choice of differentiable loss function. The objective during training is to minimize this loss. The choice of the right loss function is important, as different tasks demand different measures of error, and selecting the appropriate one is essential for achieving optimal performance. The overarching goal during training is to minimize this loss, as we have said, and the model learns by adjusting its internal parameters, which are weights and bias that we have explained before, in a way that reduces the difference between its predictions and the actual outcomes. This process is essentially an optimization task, where the model strives to find parameter values that lead to the smallest possible loss. After obtaining the predicted output through forward propagation, we evaluate how well our model is performing by calculating the loss or error. The loss quantifies the disparity between what our model predicted and the actual target output. A significant consideration in this step is the choice of a differentiable loss function, as we have explained in the previous slide. So the differentiability is crucial because it allows us to employ optimization algorithms like gradient descent, and this will enable the iterative adjustment of model parameters during the training process. The importance of selecting the right loss function cannot be overstated, as we have explained. Different tasks such as image classification, regression, or language translation require different measures of error. Choosing an appropriate loss is important. For example, we can use in regression tasks, we can use, for example, mean squared error, MSE, where the goal is to predict continuous values. Mean squared error is a common choice for loss function. It calculates the average square difference between each predicted output y hat I and the corresponding true output yi. Over a dataset of size n, the formula can be written as sum from I equal to 1 to n of the difference between the target and the predicted value square, and this the sum will be divided by n. This is the MSE. And the MSE penalizes large errors more severely due to the squaring, and minimizing this loss during training encourages the model to produce predictions that closely match the actual target values. In classification tasks, we can use, for example, cross-entropy loss, where the objective is to categorize inputs into different classes. Cross-entropy loss is a commonly used metric. It measures the dissimilarity between the predicted probability distribution y hat I and the true probability distribution yi. So the formula can be written for binary classification as follows. So it is the sum from I equal to 1 to n of yi multiplied by log of the predicted value plus 1 minus y multiplied by the log of 1 minus the predicted value of y hat I. And this loss function is designed to measure how well the predicted probabilities align with actual class labels. Minimizing the cross-entropy loss encourages the model to assign high probabilities to the correct class and low probabilities to incorrect classes. Then comes the last step of this iterative approach, which is the backpropagation. The objective of backpropagation is to fine-tune the weights of the neurons in the multi-layer perceptron based on the loss computed during forward propagation. This adjustment ensures that the network becomes proficient in accurately predicting outputs for given inputs. While the end goal, the ultimate goal, aligns with the perceptron rule, which also aims to refine weights for better predictions, backpropagation introduces a crucial distinction. The traditional perceptron relies on a step function, which is not differentiable. In contrast, backpropagation leverages activation functions that are differentiable, and this is a key difference because it allows us to calculate gradient and perform optimization, and this will facilitate the iterative refinement of the neural network parameters to minimize the loss and enhance predictive accuracy. The weight updating process follows a simple formula. So the new weights equal the old weight minus learning rate, which is mu, multiplied by the derivative of the loss according to that specific weight. Anyway, here mu represents the learning rate, which is a user-defined parameter determining the step size in weight updates. This is quite similar to the perceptron rule that we have explained in the previous part of this lecture, but with difference of derivatives here because the loss is differentiable. Anyway, so the derivative of delta Wg and the delta loss signifies actually the partial derivatives of the loss function concerning the weight Wgi, and these derivatives measures the impact of a change in the weight Wgi on the overall loss. In essence, this formula guides the gradual adjustment of weights during the backpropagation process as shown in the figure, and fine-tuning the neural network to minimize the loss and enhance its predictive capabilities. Regarding the learning rates, it is important in determining the size of these adjustments, ensuring a balance between precision and computational efficiency. Let us consider this example. In the pass-forward step, we compute the final output using this weighted sum as explained earlier in this lecture. So E5 equal to the activation function applied on U5 equal to the activation function applied to W35 multiplied by E3 plus B35 plus weight 45 multiplied by E4 plus B4 5. But here we will focus more on the backpropagation. To compute derivatives gradients with respect to parameters for all layers, we use chain rule of differentiation. For example, partial derivative of the loss regarding W35, the weight W35, is equal to the derivative of the loss according to E5 multiplied by the derivative of E5 according to U5 multiplied by derivative of U5 according to the weight 35. So here we have a chain of derivatives to compute the derivatives of the loss according to each of the weights. So here in this equation, derivative of the loss according to E5 represent the partial derivatives of the loss with respect to the output E5. It measures how a change in E5 influences the overall loss. And this is the same for other derivatives. We have the derivatives of E5 according to U5, for example, according to the activation function, and the last one according to the weight W35. Anyway, by sequentially multiplying these derivatives, we obtain the overall gradient of the loss with respect to the weight W35. This calculated gradient guides the adjustment of weights during the backpropagation process, contributing to the network's learning and optimization. If we suppose that the loss function is MSE, is mean squared error, then the partial derivative of the loss with respect to the output E5 will equal to the derivative of 1 over 2 of predicted value minus actual value minus actual loss square divided by the derivative with respect to the predicted value, which is 2 multiplied by 1 over 2 multiplied by predicted minus actual multiplied by the derivative of predicted minus actual on the derivative of predicted. And this will give, since we will reduce 2, it will be divided by 2, and the derivative of predicted minus actual is actually 1, then we will get predicted minus actual. And the predicted value is not anything but E5, minus the actual. This derivative quantifies the impacts of a change in the predicted output on the overall loss during backpropagation. If you consider that the activation function is sigmoid, phi x equal to 1 over 1 plus exponential minus x, then the derivative of E5 with respect to the activation function will be U5 multiplied by 1 minus U5. This derivative signifies how much a change in the weighted sum U5 affects the output of the sigmoid activation function. Let's go through the computation of the second partial derivative. This calculation simplifies nicely because when evaluating the derivative with respect to a specific weight W35, all other terms are constants. Constants like E3, E4, B35, and B45. They are treated as constants and therefore do not impact the differentiation with respect to W35. This simplification streamlines the computation during the backpropagation process. So let's assemble these derivatives during the chain rule to compute the final derivative. Substituting the previous derived expressions, we will have E5 minus actual multiplied by U5 multiplied by 1 minus U5 multiplied by E3. This expression represents the gradient of the loss with respect to the weight W35, as we have said before, and it provides crucial information for the backpropagation process and the adjustment of weight in the neural network. So this derivative will be multiplied, as we have said before, by the learning rate, and this will be subtracted from the old weight. This is what we will see in the next slide. Absolutely, the weight update for weight W35 is performed using the gradient calculated during backpropagation. Then the new weight 35 will be equal to the old weight 35 minus learning rate multiplied by the derivative that we have already computed. And we will only replace here the derivatives by old value E5 minus actual multiplied by U5 multiplied by 1 minus U5. Everything will be multiplied by E3. This update rule guides the gradual adjustment of the weight W35 during the training process and will contribute to overall learning of the neural network. And this should be iterative and repeated many times until we achieve the best performance. In the same way, we can backpropagate the error and update the other weights, including, for example, weight 4-5. Certainly, the weight updates for W45 follows the same principles. The chain rule is applied to compute the partial derivatives, and we will get the similar equation at the end, which is E5 minus actual multiplied by U5 multiplied by 1 minus U5 multiplied by E4. This update rule, as we have said before, will be repeated for all the weights and also iteratively using different batches, backpropagation and forward propagation, until we achieve a steady state or the best performance. We can update the weight W45 as we have done previously with W35, and the new value of W45 is the old value W45 minus learning rate multiplied by the partial derivative that we have just calculated, which is E5 minus actual multiplied by U5 multiplied by 1 minus U5 multiplied by E4. We can use the chain rule of differentiation to backpropagate the error to earlier layers. For example, here we can compute the partial derivative of the loss with respect to the weight 1, 3 as the derivative of the loss with respect to E5 multiplied by the partial derivatives of E5 with respect to U5 multiplied by the partial derivatives of U5 over E3 and so on and so forth. It's a chain that we have in the path until we have the derivatives of the U3 according to the weight 1, 3. And the same for the derivative loss of the other weights that we have in earlier layers, for example W14 or even W23 and W24. And we will use also the same rule of updates using the old weights and layering rates. The gradient descent is a widely used optimization algorithm in deep learning to iteratively update the weights of a neural network based on the gradients of the loss function. The process continues until the minimum of the loss function is approached. Here is a simple explanation of how it works. So the first step is initialization, where we start with an initial set of weights. Then we make iterative update in 2 sub-steps. The first sub-step is shuffling, when we randomly shuffle the training set to introduce randomness and avoid getting stuck in local minima. And the second sub-step is mini-batch gradient descent. For each mini-batch, a subset of the training data, we calculate the average gradient of the loss function with respect to the weights. Update the weight in the opposite direction of the gradient to move towards the minimum of the loss function. The third step is repeated. So we repeat this process until a predefined stopping criterion is met, for example, a certain number of iterations, or when the change in the loss becomes negligible, becomes very small and irrelevant. Using mini batches instead of the entire dataset in each iteration makes the computation more efficient. This approach, known as mini batch gradient descent, strikes a balance between the computational efficiency of stochastic gradient descent using one data point at a time and the stability of batch gradient descent using the entire dataset. It's a common practice in deep learning training. Stochastic gradient descent is used mainly when datasets are large. Sometimes datasets can be too large to use the entire dataset in each step of the gradient descent. So instead of using the entire dataset, we randomly pick just one data point at a time. Then for each randomly chosen data point, we perform a step of gradient descent. This means we calculate how much we need to adjust the weights based on the error for that specific data point. Stochastic gradient descent is fast and efficient. Since we are using only one data point at a time, it's computationally faster and memory efficient compared to traditional gradient descent. In addition, one advantage of using stochastic gradient descent is randomness that provides more robustness. So the stochastic nature can introduce some randomness in the update process and help the network to avoid getting stuck in local minima. It's a practical approach to training neural network, especially when dealing with massive dataset, as we have said, with large dataset where processing the entire dataset can be impractical. Let us take a look on the loss evolution in stochastic gradient descent. The loss is not always decreasing locally due to the randomness introduced by selecting a single data point at each step. The loss may not consistently decrease with every update. Locally, it might even increase occasionally. What is about the overall convergence? However, over time and with enough iterations, the stochasticity tends to balance out. The overall trend of the loss converges towards a minimum. Faster convergence for large datasets, despite the occasional fluctuations, the SGD tends to converge faster, especially when dealing with large datasets. In summary, while the loss might exhibit short-term fluctuations, stochastic gradient descent proves effective in achieving convergence over the course of training, offering efficiency advantages, especially for large datasets. One of the techniques used for good convergence of the learning is learning rate schedule. So let's discuss the importance of a learning rate schedule in the context of optimization algorithms like SGD and mini-batch gradient descent. If we have low learning rates, convergence might be slow, and optimization process may take a long time to reach the minimum. If we have higher learning rates, there is a risk of overshooting the minimum, causing the optimization process to diverge rather than converge. However, in the case of adaptive learning rates, the learning rate is gradually reduced during the training process, so the learning rates go into reduction over time. In SGD or mini-batch gradient descent, the learning rate is often adjusted over time. So, what are the benefits of adaptive adjustments? In fact, it ensures a balance between convergence speed and stability. Initially allows for larger steps to quickly navigate the search space, and as training progresses, the steps become smaller to fine-tune the parameters and converge more precisely. In essence, a well-designed learning rate schedule is crucial for optimizing the training process, preventing slow convergence or overshooting the minimum. It adapts the learning rate dynamically, striking balance between rapid progress and convergence and stability. There are many other optimizers, and each one has some characteristics and advantages. We have AdaGrade, adaptive gradient algorithm, which adapts the learning rate for each parameter based on historical gradients, and it's effective in handling sparse data but may have challenges with non-convex optimization. We have RMS-prop, and we have, for example, ADAM, which is adaptive moment estimation, which is effective in handling sparse gradient and often performs well in practice across various applications. ADAM actually combines ideas from RMS-prop and momentum optimization. Anyway, there are many optimizers that you can use, and they are easily found in different libraries implementing the deep learning models. These optimization algorithms are readily implemented in machine learning libraries, as I have said, and the task is to experiment with different optimizers and select the one that performs best for a specific application. The choice might depend on factors such as the dataset, model architecture, the nature of the optimization problem, and so on. In essence, these optimizers provide different strategies for adjusting learning rates during training, and their performance can vary based on the characteristic of the specific machine learning task at hand, and we need actually to experiment and compare different optimizers to achieve the most effective one in our application. In the training process of a neural network, there are some concepts to know. The concept of batch involves dividing the entire dataset into smaller, more manageable batches. Instead of training the model on the entire dataset at once, it processes a subset of the data during each iteration. This approach serves to reduce memory requirements and expedite the training process. For instance, if a dataset comprises 1000 data points, a batch size of 100 can be chosen. Then the model will update and learns from 100 data points at each time step, iterating through the entire dataset in smaller chunks. An epoch, on the other hand, signifies a complete pass through the entire training dataset. During one epoch, the model processes and learns from every data point in the dataset. This comprehensive iteration is a fundamental unit of the training process. After each epoch, the model's performance on a separate validation set is evaluated. This evaluation is crucial in determining whether to continue the training process or to finish. The assessment after each epoch provides insight into the model current state and guides decisions on whether further training is necessary based on the performance achieved on the validation dataset so far. There are some issues in the training. One of the major issues is overfitting that can be solved using regularization. Regularization is a crucial concept in machine learning, including multi-layer perceptrons. The primary purpose of regularization in MLP is to prevent overfitting and enhance the model's generalization performance. Overfitting occurs when a model learns not only the underlying patterns in the training data, but also captures noise and random fluctuations. This can lead to poor performance on new unseen data. When the test error is larger than the training error as shown in the figure, it indicates a situation known as overfitting. Overfitting occurs when a machine learning model learns the training data too well, capturing not only the underlying patterns as we have said, but also the noise and the random variations present in that specific dataset. It's like remembering the data instead of learning the patterns. As a result, the model does not generalize effectively to new unseen data, leading to higher errors when tested on a different dataset. Overfitting is often detected when the training error continues to decrease while the test error starts to increase or remains high. The model becomes less capable of making accurate predictions on new unseen data because it's too specialized in fitting the training examples. Multi-layer perceptrons are capable of capturing complex relationships within the training data. However, if the model becomes too complex, it may start memorizing the training data rather than learning the underlying patterns. Regularization techniques help prevent this overfitting by penalizing overly complex models. Let us consider this example. In this example, we trained two machine learning models with two nonlinear separators, a simpler one on the right and a more complex one on the left. During the training, the complex model captures intricate details and patterns in the data, while the simpler model forms a less intricate decision boundary. But how do models perform on unseen data? So overfitting is like memorizing the training inputs and reflects the capacity large enough to reproduce training data, but does poorly on test data. That's why the first model may have overfitting and will perform bad and poorly on test data. And underfitting, it's like ignoring details, not enough capacity for the available detail. So we have overfitting and underfitting, two concepts that you need to learn here. However, the surprising outcome occurs during the test phase, where the simpler model performs better on new unseen data. This counterintuitive result underscores the importance of model simplicity and the potential drawbacks of overfitting. The more complex model, despite fitting the training data closely, struggles to generalize to novel instances, highlighting the need for a balanced approach that avoids overly intricate model. In essence, this example illustrates the trade-off between the model complexity and generalization. While complex models might excel at capturing nuances in the training data, they risk overfitting and might falter when applied to new scenario. The simpler model with a more general decision boundary showcases the importance of striking a balance that promotes both like robust generalization to ensure a model effectiveness and also good accuracy. So what you should keep in memory is that more complex models have the capacity to capture intricate patterns in the training data, but they need to be carefully regularized to prevent overfitting and ensure robust performance on unseen examples. So the capacity actually is a term, a concept that means a measure of the ability to fit complex data. So increased capacity means we can make the training error small. When a model has increased capacity, it can effectively minimize the training error, the error during training. And this will allow the model to capture intricate details in the training data. However, this heightened capacity can lead to phenomenon known as overfitting that we have explained. So overfitting is like memorizing the training inputs and reflects the capacity large enough to produce training data, but does poorly on test data. So too much capacity for the available data. And underfitting, it's like ignoring details. Not enough capacity for the available details. It's important to keep in mind that the principle of balance between model complexity and generalization is crucial. While more complex models have the capacity to capture intricate patterns in the training data, they need to be carefully regularized to prevent overfitting and ensure robust performance on unseen example. And to summarize everything here, the goal is to strike a balance where the model captures essential features without being too tailored to the training data specificities. So we need to balance between capacity and generalization. One of the techniques for regularization is dropout. Dropout is an effective regularization technique in machine learning that mitigates overfitting by introducing randomness into the training process. This approach prevents units, some nodes in a layer, in some specific layers, from becoming overly dependent on each other by randomly dropping some of them during training. So in dropout, we randomly drop some of the units in the MLP layers. So the selection of which unit to drop is entirely random, with each unit having a probability P of being dropped, a parameter that can be chosen by the user. By introducing this element of randomness, dropout encourages the model to develop more robust and generalized representations, as units cannot rely too heavily on each other, on specific features or patterns. This helps prevent overfitting, where the model becomes too specialized in the training data and struggles to generalize to new examples. The comparison of training and test losses with and without dropout regularization reveals a crucial trade-off in model performance. In the absence of dropouts, the model may achieve a lower training loss by fine-tuning to the intricacies of the training data. But this can lead to overfitting and reduced performance on the test set. So with dropout regularization, which introduces randomness by dropping units during training, the training loss may be slightly higher, but the model tends to generalize better to unseen data. This means that it will perform slightly poorer in training phase, but it will generalize better and give better results on test data. Dropout acts as a preventive measure against overfitting, promoting model robustness and enhancing performance on unseen data, and this showcases its effectiveness in achieve a more balanced and generalizable neural network.